right, so today we're going to talk about vector notation. We are going to use this picture. If you guys in the class want to turn the lights out, that's fine. We're going to use this picture to kind of get us started with our notes, and then we'll go through some examples. But right now, let's go ahead and turn to our notebook. Okay, so you should have your notebook out, and we should be ready to go. We're going to look at this picture as we kind of get started. We are going to label this with today's lesson title, Introduction to Physics 2. This is vector notation. Okay. So, let's go ahead and remind ourselves, what is a vector? A vector has direction, so it is a measurement with size and direction. So size and direction. Okay. All right. So if a vector is a measurement with size and direction, what are we really looking for? It is most always shown as arrows. Okay. On a coordinate plane. So that's why in the examples that we'll look at here in a second, that's why it looks like it's on a coordinate plane, because it is. We write vectors, or we write vectors as a bold A or an A with an arrow on the end. Not always an A. Whatever letter we are thinking about. So it might be a bold A like this. That's kind of hard to do when you're just writing in your notebook. So sometimes it will be an A or the whatever letter with an arrow over the top. So let's kind of go back and look at that picture. We said we were going to use the picture to start thinking about this. We already talked about the Cartesian, the coordinate plane. Then let's look at this picture. We're going to go ahead and recreate this picture in our notebook. I did not print that one out for you, but we can recreate that picture. So if this is a graph, what do we call this line? The y-axis, right? What do we call this line? The x-axis. Okay, that's going to be important. We're going to come back to that here in just a little bit. Okay, but then our graph, our vector drawing has, I look at it again, it comes from the origin and it goes straight up. Right, and it is labeled A. So we'll come back to that picture here in a second, but let's digest what it says. All right. So this is vector A. What can you tell me about vector A already? And nothing? Nothing? Okay. All right. Well, it's one line. I heard somebody say. It does go up. Okay, so it has a positive. If this were a regular graph, it has a positive relationship. It's going up. Vectors have components. Yeah. Components. Components. So what do we know about the word components? If something is a component or a factor, then it is a part. So vectors have parts. Okay, these parts, so we probably want to write that down. Parts of a vector. Okay. And so if we're looking at vector A here, and we would write, okay, vector A, the little arrow on the top, equals, we have A sub x and A sub y. Take a guess. We talked about the coordinate plane, and we talked about a little bit how earlier you're going to use the coordinate plane. So what do you think A sub x is going to be? Well, if we have an x coordinate here, we go there. This is A sub x. So A sub x is the, in this case, 1, 2, 3, 4, 5, 6. How could you describe that in other words? A sub x is the horizontal length of the vector. So it's really convenient for us that this vector starts at 0, because all we have to do is take the x component, the x part, and that is our answer for what is the x component. Okay. So considering that the x component is just the x part of the graph, what is the y component? Right. It is the, so in this case, 1, 2, 3, 4. It is the vertical height, or vertical. Okay. So when we look at these components, what do we know about the point that is at 6 and 4 right there? If we start at the origin, the point that is at 6 and 4 is the end of our vector. Okay. All right. So let's kind of make this really obvious here. We had vector A equals A sub x, A sub y. Does that look familiar in any way? Coordinates. Yeah, the points that we had in math with coordinate planes that you thought you were going to get away from are our components of the vector. So we're going to use the components of the vector later to add them up, to add vectors. Okay? Looking at what you have here, what could you use the components of the vector to find? Uh-oh. Well, let's kind of consider, what shape is this? What kind of triangle? Choop. Yes, it is a circle, Mr. Johnson. No, it is a right triangle. Okay, so what have you done in times past to find the hypotenuse of a right triangle? Oh no, I said it. Hypotenuse. I'm asking you to think about math. Do you remember that theorem? What's it called? So let's just be really clear, and we'll go ahead and write. Use. That looks great. The components and Pythagorean theorem. Watch me spell it wrong. To find the magnitude of the vector. All right, so let's do this one as an example. Okay. So if my horizontal length is 6 and my vertical height is 4, I know that I'm going to have a sub x squared plus a sub y squared equals my vector squared. Okay, so we're just going to plug them in. 6 squared plus 4 squared equals what I'm trying to find. 36 plus 16 equals, well, let's pull out a calculator and do this math. Okay. 36 plus 16 equals 52. Am I done? Is 52 my answer? What do I need to do? Well, I need to take the square root of 52 equals just my vector magnitude. So we'll do that. It's 7.2. Alright. Now we will be using this later on in a lot of different ways. But I just want to bring that back as your notes in your notes today to make sure that we are kind of have that somewhere in our peripheral. Okay. So let's come back to this idea of components. Component parts. A sub x is the horizontal length. A sub y is the vertical height. So now it comes to our examples that we had. I gave you a little piece of paper that looks like this here in class. If you are not in class with us today, if you look in the lesson and scroll down, you can see the same image. It's just in color. Okay? So this little piece of paper, I'm going to suggest that here in class you find that piece of tape I gave you, tape it to your notebook, because you're going to want to have the examples right there in front of you, because when you want to use this on tests and quizzes and things. Okay? So we're going to kind of revert, and we're going to go back and just find the components of some of these. Okay? So vector component examples is what we're going to title it. All right. So we'll just go ahead and start with A. We have our little vector sign. What is the A sub x for this vector? So what is the horizontal length of this vector? Just one. So because if I come all the way back, it starts at -7 and goes to -6. But is it 7 whatever units long? No, it's only 1 unit long. So that horizontal length is our a sub x. What is our vertical height of a? 2. So it's just like you're finding the coordinates for. Okay. All right, so take a second and think. Okay, if a is a sub x1, a sub y2, what other vectors in your example sheet are exactly like it? B has a sub x, or b sub x is 1, b sub y is 2. Is there another one? E. E is a e sub x is 1, e sub y is 2. So these three are all exactly the same vectors. We're just looking at them. They're in a different perspective, a different place. Okay. All right. So we'll skip those as examples, but we will do C. What is the C sub x? What is the horizontal length of C? Wait, remember, he is all the way back there. Hunter, like you were being hailed. Okay, so hold on. Greenwood. I do? Yes, ma'am. Austin, the student services want you for your schedule. Okay. So remember, the x component is the horizontal length. So when we look at C, what is the horizontal length of C? 1, 2, 3, right? And what is the vertical height of C? 1. Okay. So remember, we could find the length of C by using that Pythagorean theorem, which we'll come back and do a little bit later on. But let's look at D, since it is different. What is the x component of the D vector? 1, 2, 3, 4, 5, right? And what is the y component of the D vector? Just 1. All right, we'll go ahead and do F since it's the last one that's different. Vector F. What is the x component of vector F? 2. What is the y component of vector F? 3. Okay, so when we're talking about vectors, those components are the parts that make up that vector. When we calculate them, when we would add them, use that Pythagorean theorem, then we can find the magnitude. So the length of that vector, we have to use these component parts for. That was not even mine. We have give me a thumbs up if you feel like you understand that. That makes pretty good sense. Okay. All right. We're going to add 2 words to the end of this. And then, I'm not exactly sure even why I put these 2 words on here, but we are going to define distance and displacement. Kind of just thrown in there, but we're going to start using them a lot. Displacement. Distance is how far traveled. How far you actually went. This is a scalar measurement. Displacement is the difference between start and finish. Okay? So think about where were you Tuesday afternoon about the same time? Well, okay, but most of us were right here, weren't you? Most of us were. I was, anyways. So if I was right here Tuesday afternoon, did I stay here for 48 hours just to be here for you guys today? No. I went home, I came back, I went home again, I came back again, I went and got lunch, all these kinds of things, right? So my distance might have been like 30 miles, but my displacement is 0 because I'm right back where I started. There is no difference between Tuesday afternoon and right now. Does that make sense? Huh? What? Other than the lesson? Well, what? Don't understand what you mean. Oh yeah, but I mean like my physical location. Like I've same place, same seat. Okay, so we want to kind of think about that. We could put a little drawing with it to make sure we think about our coordinate plane again. Okay, if I started here, okay, we'll kind of change it a little bit, and I went this way and down and around and up and over, and I ended right here. This is my distance. But what's the displacement of that? Have you ever heard anybody say the shortest way to get from point A to point B is a straight line? That's your displacement. Okay, if I walked all this way, whatever, but my displacement is still the difference between. So we want to be mindful of those two words and keep them separate. How many of you are tired of hearing me talk? I thought I'd have way more hands than that. Let's go ahead and stop the notes part anyways.